Hi, my name is Stefanos, and today I'm going to talk to you over some perspectives over the next generation of compute at the consumer edge with a paper called The Future of Consumer Edge AI Computing. Right, a few things about myself. My name is Stefanos. I also go by Steve, and I'm a machine learning researcher currently at Brave, which is a web company created by the founder of JavaScript. At the moment, I'm also a visiting researcher in the University of Cambridge, and I did my MPhil there as well. Before Brave, I used to be a research scientist at Samsung AI Center in Cambridge, and prior to that, an engineer at CERN in Switzerland. And broadly speaking, my research interests revolve around the areas of distributed and mobile systems, efficient deep learning, as well as federated learning as a manifestation of distributed ML. Lately, I've also been tapping into the area of generative AI and LLMs. Right, so this is an outline of my talk today. I'm going to start with some background about the current state of play with respect to deploying machine learning on devices and the respective machine learning workloads. I'm also going to highlight the current challenges that we face and where previous compute paradigms are falling short of. Next, I'm going to present a new paradigm of compute for organizing resources at the consumer edge, for example, a consumer's home, going through the design foundations of this model, as well as reference architecture and related technologies that facilitate the realization of this model. Last, I'm going to talk about some upcoming use cases that will be made possible through that change in organization of resources and present some open challenges and future directions that can fuel research of tomorrow. Uh, Please feel free to interrupt me in case something is unclear or you have any questions, and some will let me know if there is a raised hand or like a question in the chat. Right. Let's start with some background and motivation for why we need a new compute paradigm. So it has been said again and again that deep neural networks are getting larger in their pursuit of higher accuracies and new use cases. This is truer than ever before. And as we enter the new era of hyperscale foundation models that effectively show sparks of intelligence, as model increases, model size increase, so does the hardware that we have available, both in the data center as well as at the edge. So we have, for example, NVIDIA H100s fueling the cloud setting, or like the recently announced Qualcomm Snapdragon 8 Gen 3, which is quite a mouthful for a product. But both promises significant performance bumps in generative models, training, and inference, respectively. Right. So at the same time, we have novel workloads making their appearance by the day, ranging from like self-driving with Tesla FSD to image generation with an example being Adobe Firefly. We have also at Brave launched our own AI assistant called Leo for interaction with the web page, and you can also see use cases from ranging like doing creative writing, such as Grammarly. Several cases also make their way into the mobile too. A prominent example being the Google Voice Assistant being launched on Pixel 8. Right. So there has definitely been an accelerated pace of advancements lately in the area of AI, be it in the form of different architectures that push the state of the art, in the form of large language models such as ChatGPT or the GitHub Copilot. You have diffusion models and Dolly, or even nerves for realistic scene modeling. Simultaneously, more and more deep neural networks are being deployed, and they reside at the same time on device, both inside the premises of one application and even across applications. So indicatively, more than 50 models can reside in the same device at the same time, not all running at the same time, obviously. Last, privacy becomes increasingly important, and regulators are pushing towards on-device solutions for preserving the privacy of users' data, and yeah, it is also for it is both for private inference as well as for training and personalization. So all these push the resource requirements of being smart to a higher baseline than we had before. So generally speaking, there is a pendulum effect in terms of hardware development lifecycle at the macroscopic level. First, hardware breakthroughs appear in the data center and accelerate workloads that were previously intractable. ML related examples include various accelerators such as GPUs, ASICs such as like the Google TPU, or FPGAs. Subsequently, hardware becomes more compact and more cost effective, let's say, to deploy, and it makes its way towards the consumer world. Examples of ML related stuff include various system on chip accelerators, such as NPUs or even the Edge TPU. Last, this cycle is complete by workloads scaling up in their requirements, and it necessitates new hardware breakthroughs in order to execute these types of new workloads. And thus, the workload cycle starts all over again. Right. So at the moment, we are at the tick phase. So we can run and serve new workloads from cloud resources, but not locally, as hardware resources lag behind in scale compared to the workloads that are appearing. Execution is largely bottlenecked by the current hardware, and the current hardware at the edge remains organized in silos, both in terms of compute and in terms of like data or context. Right, so let's go through each one in more detail. So in the past, deep neural network workloads have been largely enabled through the advancements in accelerator hardware design at an acceptable cost. Undoubtedly, GPU hardware has made its impact towards deploying machine learning in the wild. However, lately, computational advances scale slower than the new model requirements as we're entering the era of large-scale models or foundation models. And as such, we constantly need to devise new solutions, algorithmic solutions, or ride the accuracy versus latency trade-off wave in order to be able to even run these models. And examples of such techniques include mixture of experts for or quantization and low rank approximations for dropping effectively the memory requirements for these models for inference over training. We have speculative decoding or token skipping that are more specific to LLM use cases, or we have started seeing workload offloading use cases for effectively using remote resources in order to be able to run these workloads. Right. A second problem that we have is the memory becoming a bottleneck. Effectively, the inference workload of foundation models, including large language models, is largely memory bound. This is wrong. This means that effectively the CPU or the GPU is waiting for weights to be fetched from the off-chip memory into the on-chip memory, the off-chip memory being DRAM. And this is very costly, both in terms of latency and in terms of energy. Just to illustrate that the energy impact, it is more than 100 times higher consumption than computation to bring memory from to bring the weights from DRAM, from off-chip memory, while on-chip caches often account for 50% of the processor's energy budget. This also spans into training, which becomes relevant, for example, in federated learning use cases, where if you want to train a small bird on device, it can consume more than 8 gigabytes of peak memory, while inference require 1/16 of that. And a typical way of effectively using these weights is through bumping up the batch sizes. However, this is not immediately realizable at the edge because of memory, and or the use case at hand. So if you're doing um, well, next word prediction or like generation through an AI assistant, then you don't really have like the batching as a solution. Um, right. So last, devices remain largely isolated, and they replicate similar setups in terms of their hardware or sensors without leveraging the coexistence of other devices in their ecosystem, in their network. Information remains siloed inside each device, and there is point-to-point communication only opportunistically, if any. For example, and a prime example is like the Apple handoff feature between devices of the same ecosystem. Therefore, the current landscape lacks a common data and compute interconnect that hinders many use cases from being realized. Right. Yeah. Collaboration is not a new thing in the literature, and there have been various computational paradigms running for running AI at the edge, be it in the form of on-device execution, cloud or edge collaboration, local area network synergy for computing, or even volunteer computing for volunteering your spare compute cycles for scientific purposes. However, each one comes with its own set of drawbacks, be it in terms of scalability or privacy, because effectively you're running something on somebody else's computer, and making them not ideal for the trends, the computational trends we just saw. So, for this reason, we propose a new paradigm of organizing compute at the edge, centered around the presence of the device hubs. These are hubs that can be either standalone or collocated with other devices in the network, and can enable offloading and coordination of the setting of compute and context without sacrificing on privacy. So, at the consumer edge, there are various smart devices residing in the network, each with its own resource availability. Like if you take an example of how many devices are currently connected in your house, it would be probably in the tens or even twenties if you're like me. Therefore, you have various hardware with resources that are able to offer their cycles, and you have various tasks that need to be executed. Um, Therefore, we can draw a parallel of this like allocation or scheduling problem from ML tasks to resources, subject to a specific budget. And you can think about this as a generalized knapsack problem, where we allocate ML tasks to device resources subject to certain limitations, such as latency budgets, or energy budgets, or device availability, thermal behavior of devices. Also, you should think about the devices themselves are not pure accelerators that are waiting to run some extra workload, but they have their own use cases, and so quality of experience for the user is of utmost importance. So, apart from the collaboration that you just saw and the allocation of resources to devices, there are various collaboration links created spanning across two or more individual devices that belong to potentially different custodians, different users. At the same time, there are different privacy zones that limit what collaborations can actually happen between devices, and we'll revisit this very topic in later slide. So our paradigm is based on four pillars, namely shared compute and context, privacy, as well as sustainability. So there are various components realizing each of these pillars in our paradigm, and we'll go through each one of these in more detail. So, in terms of compute, we envision the change from like having duplicate, highly specific hardware accelerators that exist on each device nowadays into a more central device hub that enables or accelerates AI tasks. These offer larger budgets in terms of area and thermal dissipation that you can have, as well as power budget. Um, they are not restricted by the limitations that you have on like a mobile system, for example, or even the passive cooling that these devices have. Moreover, you can have like this hardware being reconfigurable or even extensible in order to future-proof it. Um, so compute partitioning can be discussed on two levels, one being static partitioning of resources. So this is more related from the standpoint of a device manufacturer, such as Samsung. So, and it relates to the problem of where to put certain accelerators and of what dynamic this accelerator should be. And the other one is in the product lineup, I mean. And the other one is the more dynamic split of workloads, effectively where to run what on demand based on the nature of AI task, the urgency to complete, as well as the intersection of tasks between devices. These need to be carefully considered so that replication is minimized, but you don't want to strip a device out of any meaningful computational capability. It is crucial in the presence of multiple devices also that a multi-channel communication is supported so that you're both able to communicate with all the available resources as well as that you're able to be able to split the bandwidth in a quality of experience aware manner. And the tasks, and last, the tasks need to be preemptible so that you're able to support higher priority tasks without hurting the user experience. An example could be that you just returned from like some holidays and you took some pictures on your phone. So in the background, you might have like some classification task running for like classifying what the image is representing or like which people are inside the picture, and then you want to see like a series on Netflix, for example. So you don't want this classification task to hinder your experience with Netflix. This is very coarsely put. Right. In terms of context sharing, there is effectively a contextual fabric of information that can be shared across devices. This contextual sharing, can be twofold. One is the explicit context sharing, and we're talking about raw data, raw sensor data, or it can be implicit in terms of like embedding this information into a common subspace in order for models to be able to use that in a multimodal setting, for example. Collaborative learning and multi-perspective inference can be enabled through this shared context and created through ecosystem at the edge rather than having a bunch of devices that you just bought. And this ecosystem leverages sensors and data across devices and potentially across users. Last but not least, devices can leverage this shared context for their own tasks. So not only to collaborate, but also to enhance the task that they would originally fulfill. And yeah, there are multiple use cases that you could deploy that into. So imagine, for example, that you just walked into your apartment, like your living room, and you just I don't know, talk to a voice assistant such as Alexa, or like you're carrying like your smartwatch, which I'm not sure it's even visible in this image, but yeah, the guy's is wearing a smartwatch. So this interaction could just preload. You could detect which person is inside the living room and preload certain preferences or even their user profile on like the TV. At the same time, you have various agents inside or devices in the at home, and they can fulfill multiple roles in different settings. So, for example, you might have a surveillance camera for security, and you can enhance this with a voice assistant, or like you can combine this with a robotic vacuum cleaner in order to be able to do some active scanning of the room. At the same time, you might use all of these for pet surveillance if you are not at home. Right. Next, let's talk about privacy. Privacy is thought to be not just a checkbox that need to be ticked inside the product specification, but we like to think about privacy as a continuous spectrum, effectively a privacy budget. And privacy manifests in different ways for different tasks. So if we're talking about inference, then the inputs and outputs of the network, along with the intermediate representations, if we're talking about partial offloading of the inference to a remote endpoint, they become sensitive. On the other hand, at the training time, the model parameters as well as the gradients become also privacy sensitive because they might leak data about the dataset that the model has been trained on. Simultaneously, not all data are equally sensitive to all parties, and this is what effectively creates these privacy zones that we talked about. So the trust zones. For example, you might have these holidays photos that you're willing to share with your family, but not necessarily with a third-party provider, such as Google. Or at the like in the the inverse is like that you have your browsing history that you are potentially willing to share with a third party, but not necessarily with your family. So these trust zones shape the collaboration opportunities and access levels between devices. And this is bringing this topic back to the trust zones and collaboration opportunities that we talked about. Last, scaling and replicating compute can easily get out of hand. Thus, we need to be wary of the environment and the fact that computation at the edge might not be as optimized as large data centers. And thus, we want to offset the overhead, the environmental overhead of running things at scale at the edge by using techniques by deploying techniques from efficient ML, whether they are architectural, representational, or executional. Also, um, this model enables less replication and higher utilization of chips that are allocated per device, because effectively you don't replicate standalone chips everywhere, just in case you might need them. And last, we bring the idea of device upcycling at the forefront of our paradigm as a means of using previous devices that are still usable and minimizing the e-waste. So previous devices that might be 2 years old can still be useful both as sensors as as well as to provide certain computational ability to the edge. However, this needs support from the manufacturer so that the manufacturer either opens up the firmware and enables third party or like the open source community to be able to contribute security updates or like to provide the security updates on their own. And there are various incentive problems there. Right. Before I move into the architecture, are there any questions?
Yeah, let me just quickly remind you that if you have any question, please either raise your hand or just post it in the chat, and then I'll try to unmute you. See, there's
Right.
something that would be. All right, at the moment we do not have any questions.
All right. Assume that we don't have any right now. Right now so let's switch to the reference architecture of this paradigm that we're talking about. So how would one implement that in practice? So here we depict the reference architecture of an orchestrator. The orchestrator is the central entity that coordinates compute and context sharing across devices. This can be residing inside the Edge AI hub or co-located with another resident device. This could be, for example, your TV, which is always there, and it can host like a capable chip on a large area, on a large surface. Moreover, there can be primary or secondary orchestrators in case that you have high loads, so for load balancing, as well as for fault tolerance. The role of the coordinator is to manage and monitor the resources, schedule jobs per device, handle task preemption and migration, as well as to be the gatekeeper of permissions to different data sources. One might ask why not go with a peer-to-peer architecture, and this is a perfectly valid question if you ask me. So the reason is that devices at the edge may not be always available, especially mobile devices. which can cause data inconsistencies as well as model staleness if we're talking about like model personalization or training. Therefore, the peer-to-peer architecture would be significantly more complicated to implement and to guarantee robustness on top of it. Next, the reference architecture for the Edge AI Hub is presented, and it touches across multiple layers of the technology stack, ranging like from the application layer to the bare metal. So starting from the hardware, we propose the integration of general purpose as well as specialized hardware, for example, NPUs, which are much more energy efficient to run these workloads, optimized for a broader set of machine learning operations. We would like to have a multi-precision arithmetic along with sparsity, support for sparse operations and dynamic input length. In terms of memory, we need large multi-level memory for training and performing inference on large models, such as foundation models. And DMA support for a zero copy in distributed ML use cases. Last, applications unboxing and visualization for fast context switching are enables for preemptible and siloed tasks. In terms of network, as I said before, we need to have multi-channel communications for load balancing and for increased throughput through MIMO is a requirement effectively for several use cases, for several distributed use cases. Next, as data are the first, as data are the first class citizen in machine learning, we continue to need hierarchical solutions with fast caching potential, along with implementing access control lists for privacy and permissions management. Moreover, we would like to have redundancy over the data that are used across devices, and this can be guaranteed over a RAID if we're talking about disks or even distributed replication across devices at the local edge. The operating system on top of this is responsible for the local resource management and task scheduling. And on top of that, we have the low and high level machine learning libraries. The low level being like CUDA or like the NN API in Android, which implements effectively the operators closer to the hardware, or you can have like BLAS and GEM libraries. And then on top of that, you have the high level libraries that most of us are programming in. On top of that, we have the middleware that implements whatever we talked about. So the preemptive scheduler, the performance and power monitoring, and so on and so forth. And yeah, this is how different applications ranging from like virtual reality to like semantic segmentation or next generation of voice assistants can be realized. So here we depict several technologies that can help realize these aforementioned goals, and many fields of which are being actively worked at in my previous and current teams, signifying with a star. So let's go through some of them quite quickly. So on the model serving side, we have recently presented fluid batching at ICCAD 2023, end of October or start of November, which comprises of a model early exit aware scheduling algorithm for serving preemptible inference requests at the edge or cloud. These are preemptible because of the early exit nature of the workload. So alongside, we propose an NPU design for efficient execution of this system. So just to make clear, early exit architectures are effectively architectures that have intermediate checkpoints or exits, and you're able to classify or get a result by earlier representation of the features in a preemptible manner. So you don't have to use the rest of the network. On the offloading side, we have mostly worked in the past on two systems, namely Spin and Dyno. The former couples early exit networks with offloading for synergistic execution of network across device and edge. And Dyno handles a similar task, that of unloading, effectively pushing computation from the cloud to device in a configurable precision of intermediate representations manner. In terms of dynamic workloads and early exiting, our group has published several lines of work, including a survey paper on various applications of early exit networks in the literature, spanning also across transformer architectures. Happy was the first line of work that we did, and was implementing a hardware-aware design of the architecture and exit policy of early exit deep neural networks. Persephone was a system that personalized these early exit predictors to local distributions of data, and thus making the multi-exit deep neural network more efficient or accurate for local inference. And last, multi-exit segmentation designed early exit networks for the non-trivial dense task of semantic segmentation. In terms of collaborative learning, our work has been in the past mostly focused on federated learning solutions that tackle the system heterogeneity in cross-device FL, with Fjord as a resource-aware training scheme based on order dropout, and Fedoras, a resource-aware federated NAS solution, utilizing effectively a search space as a knowledge-sharing backend and tuning what is distributed to individual devices based on their capabilities in order to be able to train and contribute to the knowledge base. Um, in terms of model compression, we have also worked with Samuel as well on model compression through Maestro, and it's going to appear in Want AI workshop at NeurIPS. And it proposes a method for trainable low-rank decomposition of per layer, and this is configurable through order dropout on the decomposed matrices of each layer. So each layer can have its own rank, and it progressively gets shrunk based on certain techniques, let's say. This yields gains in general, both in training as well as inference. Last, in terms of like, it is crucial that we do app-specific benchmarking for finding bottlenecks and optimizing in an informed manner. To this direction, we have published a paper at IMC where we benchmarked ML-based applications from the Play Store and how they are running on various devices from different tiers, both in terms of performance and in terms of like energy consumption. So all this should lay the groundwork for enabling forward-looking use cases that span across the borders of single devices. So in terms of upcoming use cases, specifically, we can have next generation of virtual assistants with enhanced interaction, multimodal interaction. So you can have, for example, both visual as well as voice interaction, and you can have long contexts that are able to personalize the discussion of the voice assistant to the user at hand. Also, like the long context spanning more than, let's say, the typical, not the typical, but like the top end being 100,000 tokens to being able to recollect individual previous past experiences and personalize the discussion on that, or adapt the discussion towards that. In terms of virtual spaces and virtual reality or augmented reality, we have had the promise of metaverse laying around for a while. This can be used for entertainment or professional purposes. The professional purposes being having been more profound, like during COVID times. On the inverse, instead of us moving towards the virtual spaces, we have cyber physical agents moving to the real space. So we have, for example, nowadays robotic assistants or even robotic vacuum cleaners. And through this paradigm that we're proposing, you're able to train or adapt the robotic assistants to, for example, like the setting of a specific home. And this context could be leveraged across homes in order to make, for example, obstacle avoidance more robust across settings in a federated manner, for example, in a private aware one. And last, there are use cases for e-health. So during COVID times, we saw that gyms were closing down, and if you wanted to like have a fitness assistant, then you would be able effectively to do that at home. So you could have like monitoring of your exercises across various with vision and across various sensors, and you will be able to monitor your health or your fitness um, through multimodal sensors. The e-health spans also across like medical records. It can also span to your meal preparation and automating that, and like effectively bind all of this into a common subspace that can be leveraged across for a holistic way of managing your health electronically, at least, or virtually. However, this is not a straight line towards realizing. So we have certain challenges that lie ahead, and these give opportunities and future directions for that can fuel research of today and tomorrow. So in terms of machine learning challenges, first of all, we have, like we talked about, many devices, but these devices don't necessarily have like identically distributed data, and they are potentially solving different tasks, right? So we need to borrow or extend solutions from like domain adaptation, federated learning, and continual learning fields in order to be able to tackle this problem. Moreover, the current state of the edge is described by a general lack of annotated data. Unless we're talking about tasks that don't really need annotations, such as next word prediction, because we have text that gets filled, we need to leverage techniques from semi or unsupervised learning. Or if we talk about like being able to at least tag certain data, we would be talking about active learning techniques. So like select which data to be annotated. More interestingly, this can manifest in robotic settings where you have like a static agent, for example, a surveillance camera, and you have a mobile agent, such as a robotic vacuum cleaner, and you can effectively send the robotic vacuum cleaner in order to be able to get the data that you want in order to train locally. As said in the beginning, we're living in an era where our are filled with models, and these models run potentially at the same time. So we need to be able to schedule them efficiently. We need to leverage like the task relatedness in order to potentially weight share the backbones across these tasks, and to be able to preempt workloads while they're running in order not to hinder the user experience. In terms of, well, right now I'm going to talk about federated learning. You have a tension between global and private utility as well as privacy. So this trade-off between optimization objectives that might be running at the same time should be more carefully studied. Next, in terms of privacy, we also have the right to be forgotten. So you have large models being trained on trillions of tokens, and we want both due to regulation, but also due to like the just right of the user to be forgotten, not to have like long-term persistence of their data, to be able to remove their data from the knowledge of a model. So model unlearning becomes like very relevant and timely towards this setting. And last, we talked about assistants that have a physical manifestation in the real world, like robotics. So when they're taking an action, they have real consequences. So we need to be able to have interpretable models, as well as models that are able to assess the confidence of their actions, and potentially argue about their planning in a chain of thought kind of way. Last, we have system level challenges, such as the system heterogeneity and availability at the edge. So we don't have, we like at the edge, we don't have in the consumer world, we don't have highly available servers that run all the time. So we need to take this robustness under partial participation. We need to guarantee robustness under partial participation and graceful recovery, as well as idempotence of tasks. Moreover, this needs to be done in a transparent way to the user so that they continue to use the system. In terms of interoperability, we talked about various devices in an ecosystem collaborating. However, we're wary that we're aware that like these devices might not be coming just from one provider, but multiple ones. So it is crucial that we standardize certain interfaces. We enforce like some backward compatibility so that devices of previous generations are still able to communicate with future ones, and to open up the middleware in order to be able to have a secure ecosystem that is able to be developed as we go. And this points towards an incentivization mechanism, both for manufacturers to support old devices or old devices from several years ago, or even to incentivize the opening of like their previous investments, just for the open source community to be able to um, maintain that. And also for clients to be able to, not to be able, but to accept the execution of workloads on premises, because at the end of the day, they're dedicating their resources and they're footing the energy bill. So with that, I would like to conclude. I would like to give a shout out to my wonderful collaborators. This was work largely done while working at Samsung AI Center in Cambridge. And thanks. Let me know if you have any questions. And in general, we're hiring interns during the summer at Brave, so feel free to reach out or apply.
Thank you, Steve. So please, if you have any questions, just either raise your hand or just post the question to the chat, and then Steve can answer. Yeah. Maybe I would start with a couple questions. So you mentioned at the beginning that as like historically the main driver of like machine learning capabilities was in increasing compute and mainly through GPUs. So what do you think would be, or what do you expect that would be the main driver in the kind of era of edge computing?
So it will definitely be like hardware. Without hardware, you cannot execute stuff. It's just that you're able to leverage distributed resources that already exist there. Definitely, we live in an era right now where the algorithms scale faster than the hardware, and hardware is not available actually. So you might have the capabilities to manufacture this hardware, but you don't have the throughput, the manufacturing throughput, to do so. So yeah, I think that at the edge, you definitely need to leverage like the multiple resources in order to be able to realize certain use cases. And use cases are going to be the driver. So it is all about context at the edge. You don't necessarily need, let's say, a general purpose assistant to help you with everything, but you need an assistant that is able to leverage knowledge that you have already persistent in your like pocket computer in order to provide you with relevant information and like personalized information.
Yeah, thank you. Yeah, maybe also along this, yeah, maybe what do you think, like, in order to kind of reach or to get to this edge computing 2.0, what is okay, let me finish the question. Now we have a raised hand by now Teresa. So what do you think is like kind of the best way to achieve this like compatibility among devices, maybe in terms of like who should be the kind of this trusted orchestrator, and how to ensure that, yeah, like you can run stuff on the devices that comes from like the different companies, and how to make sure that they are incentivized to make everything compatible.
That's a really good question. That's a really good
Yeah.
question. Um, so there needs to be like a situation where it is win-win for everybody to be able to leverage that. Right now it hasn't happened because obviously there is no incentive from like the provider to do so. Imagine also like that if you're going to open source something, then effectively you're opening your software that you have invested many millions of dollars for certain years to the public eye. I'm more of the like personally, I'm more into the open source kind of way of developing, and that like all bugs are shallow under the public eye. However, like accepting that this is not the norm for everybody, there might be subscription services where you have like a device that like is of certain years old, and then you can pay certain amount in order to be able to get security updates for a longer period of time. And this is also applying for standardization, like to be able to support different standards. This is already happening in terms of IoT with several standards, and this can span also across devices that you used to have.
Yeah. So maybe let me quickly, because I think you already kind of touched upon that, but maybe one quick question along these lines. So what do you think should be kind of the economy of the edge computing in terms of like who is the model owner, who should benefit from that? Because eventually, like, okay, you have a company or you have an orchestrator that kind of develops the model, but at the end of the day, you are the one who's giving up your data in order to improve the model. So the question is whether should you get paid or should you pay for a service and things like that. So what do you think is the right way to design a good economy of the edge computing?
Yeah, good question again, and it's very relevant in the federated learning scenarios where you're contributing cycles and data, not data, raw data, but like gradients, in order to train like something for the greater good. I think the users should be incentivized in terms of getting something out of like these training cycles, or like effectively paying the electricity bill at the end of the day. Whereas the provider should, like their remuneration, if you want, should be a better product. That it's plain as that. If you offer a better product that more users are adopting, that's enough of a of a reason to do so.
Thank you. So now we have two questions from the audience. First, let me unmute Navid Reza. So you should be able to unmute yourself, and please go ahead. Yeah.
Hi.
Yeah. First, I would like to thank you very much for your very nice talk. I have a question regarding, as you also mentioned, that there will be challenges with the heterogeneity of the IoT devices or edge devices in general, as well as the preemption and fault tolerance of those devices. It seems to me that there is a need for co-optimizing the orchestration framework as well as the co-designing the orchestration framework and the machine learning model itself. I wanted to see if you also share the same intuition or not.
So there is the heterogeneity that is inherent on a snapshot of like the ecosystem. So if you take a picture of like the devices that I have right now at my home, there are multiple dynamics of the tiers of devices, let's say. And there is also the temporal dimension. So as we evolve, we get more capable devices. So this becomes effectively more heterogeneous. So on the one hand, we have how to tackle the situation today, and then how to extend the situation tomorrow. In terms of the code design, I generally agree. I don't think anything is really static in the way that like the workloads are not static, the resources are not static. Just not only just because you have heterogeneous resources, but you have a dynamic workload. So your phone, for example, is not just a resource that you're using as an accelerator. It's not a GPU sitting on your pocket. You're using it for several things. So you need to account for the other things that are running that are potentially of higher value than your workload. It needs to be adaptable, but not necessarily co-designed. That's my view right now, in the sense that it should be adaptable to span across several tiers of devices and several generations of neural networks. Maybe the co-design could be like of the orchestrator with the underlying hardware of the device hub, because the orchestrator is effectively what coordinates the whole infrastructure. So you need to tune very well with the underlying hardware there.
Yep. Just to add a bit of more content to my question, for example, because we need to somehow distribute the model across multiple devices, right? So the model itself should have this capability to be distributed so that it would be compute and communication efficient. So my question was going to that direction, but again, thank you for your response.
Yeah, and there has been work actually for incrementally setting the model itself in order to be able to do computations, pipelining the transfer. So you transfer certain weights, you're able to do the compute while you're transferring the rest of the backbone. But yeah.
Thank you.
Cheers. Thanks for the question.
There's a question from Razvan Mihai, so please go ahead. You should be able to unmute yourself.
Hi, hello. Hi, Stephen. Thanks very much for the nice talk. So my question would be more into the direction of networking. So you have briefly touched upon in the reference architecture that the network should support some simultaneous communications over several interfaces. My question would be if when you worked on collaborative learning, if you have experienced any issues or what challenges have you seen on the networking part when talking about distributing models, about doing distributed inference or training? What were the challenges that you have seen? And yeah.
Right. Yeah. Well, doing research is a series of challenges that you need to overcome. So in the networking space, yes, especially like when we're talking about wireless communication, like I don't expect Ethernet cables to be lying around in houses anymore. So Wi-Fi is robust, but not full, let's say fail-proof. So depending on the setting, you might have packet loss, or you might have reconnections, or you might have even devices themselves being made unavailable at certain periods of time. So imagine, for example, that you have your smartwatch on you and you just go like out of your house for a while and then you come back. So this availability creates problems, or lack of availability, or intermittent availability. So this gives way into workloads that can run opportunistically, meaning that you run something as fast as you can, and then you effectively refine your result as you have more availability. This is more on the ML side of things. So early exits, for example, are like that. You might be able to get a coarse result fast, and then you might be able to refine as you have the device more available. So I talked about disconnections, noise environments on the noise is the other side of the coin for Wi-Fi, but it's not that persistent as we have seen it. If we talk about long range, if we talk about, for example, a multi-tier offloading scenario where you have some things offloading at the edge, and then the second hop would be to offload to either like a 5G cell tower or to the cloud. There you might have like more degrees of failure that you might need to take into consideration when you're offloading.
Okay, so if I may come with a follow-up, so you also see that offloading towards cloud is possible, right? So the machine learning model doesn't have to be fully deployed on-prem, let's say, so across your whole devices, but it may be the situation that you have some component of the model that is running in some cloud or in some data center, right? I mean,
yes, of course. It's not a replacement for the cloud. I mean, I don't expect any regular house to be able to host like a multi-billion parameter model on premise. Not only because like it's costly to do so, but like even the hardware investment that you need to do in order to support such a workload does not make sense, right? So the edge is definitely the way to go for certain scenarios, but not a total replacement for the cloud.
Okay. Thanks so much. Thank you.